Hi, I'm Pritham, and I'll be speaking about our work on distributional generalization, which is a new kind of generalization. And this is joint work with my colleague Yamini at Harvard. So the motivation for this work is to better understand supervised learning. So the setup here is we have some distribution D on inputs X and labels Y. And the key objects are classifiers, which are functions from the input space to the label space, and learning procedures, which are functions which take in train samples and output classifiers. Now, oftentimes in machine learning, we study classifiers only through single scalar metrics like the test error. But classifiers are actually entire functions from X to Y, and we could hope to know more about this function than just its test error. For example, suppose we know F has 40% test error. Well, there are many ways to get 40% error, and we might want to know which one we actually get. So in this work, we'll take a closer look at the classifiers as functions and show that we can actually answer some of these questions in certain settings. And to do so, we'll introduce a notion of generalization that goes beyond error. First, a motivating experiment. Suppose we have the following somewhat weird binary classification problem. The distribution on X and Y is as follows. X is a random CIFAR10 image, and Y is binary and Bernoulli depending on the type of X. So explicitly, all of the planes are labeled 0, but 10% of cars are labeled 1, 20% of birds are labeled 1, 30% of cats are 1, and so on. In other words, this is the joint distribution of inputs X and labels Y of the train set. Now, suppose we sample from this distribution and train a ResNet to fit this train set and to predict the binary label Y given the input X. Now, the question is, what happens at test time? So given a new image of a cat, say, how does the classifier behave? And it turns out that trained classifiers reproduce almost the exact same distribution as the train set. So in this example, for example, if the 30% of cats on the train set are labeled 1, then it turns out that the classifier predicts 1 on roughly 30% of cats at test time. And similarly for all of the other subclasses. So in other words, the joint distribution of X and Y on the train set is close to the joint distribution of X and predictions f of X in a certain sense on the test set. So why is this surprising? Well, we use a method designed for classification, but we don't actually get a good classifier. So the Bayes optimal classifier in this setting would be the function which outputs 0 on the first 5 classes and 1 on the next 5 classes. This is a function with lowest test error. But we don't get this. We get a function with much higher test error, but in fact, something that looks like an approximate sampler. So the trained classifier produces samples such that f of x looks like a sample from the true conditional distribution p of y given x. Now, this is just one experiment, and I haven't formalized this yet, but it turns out that similar kinds of behaviors happen not only for neural networks, but also for kernel methods and decision trees in certain settings. And notice here that there is actually a large generalization gap because we fit the train set to train error 0, but the test error is high. But on the other hand, even though the generalization gap in the classical sense is large, there is a certain other kind of generalization going on here. There's generalization in a certain distributional sense, which we'll formalize. Okay, but already in this experiment, we can see some implications of our conjectures. One implication is that it means that overfitting is not always benign. In fact, we show many realistic settings like this one here, where fitting noise on the train set causes the classifier to reproduce that exact same kind of noise at test time. And so interpolation here is not always benign. And the second implication is that interpolating neural networks are not consistent, especially in settings where there's some Bayes risk. For example, in this setting, the interpolating neural network does not converge to the Bayes optimal classifier and will not converge to it even with growing numbers of samples. And this is sort of an empirical converse to this other result that also appears in the same workshop, which is that not interpolating neural networks are consistent. Okay, So to capture these behaviors, we introduced this definition of distributional generalization, where the idea is that the joint distribution of inputs x and predictions f of x on the trained set is close to the joint distribution of inputs and predictions on the test set. Now, this definition lets us specify the exact form of distributional closeness that we want to use. And for a particular choice of closeness, this definition reduces to classical generalization, because classically we just say that the error on the trained set is close to the error on the test set. But these two joint distributions could be closed in many other ways. And in the paper, we give two formal conjectures which explicitly lay out the form of distributional closeness that is empirically satisfied. Now, the agreement property is actually completely different behavior than what we've seen so far in the experiments. I won't talk about it here, but that's because there's actually this other paper that also appears in this workshop that builds on our work on the agreement property. So if you want to know more about the agreement property, you should read this paper instead. But now we'll talk a bit more about feature calibration informally. Okay, so the feature calibration conjecture says that the marginal distribution of classifier outputs f of x and two labels y match when conditioned on any good subgroup. So in this example from before, cats formed a good subgroup. And so this conjecture means that the marginal distribution of predictions conditioned on x being a cat is close to the marginal distribution of two labels conditioned on x being a cat. So if 10% of cats are labeled 1 in the train set, then 10% of cats will be predicted to be 1 on the test set. Now, of course, the question here is, what do we mean by a good subgroup? And we define a good subgroup roughly to be subgroups which are themselves learnable using the exact same training procedure. So the intuition here is that cats were a good subgroup for ResNets because ResNets could have been trained to distinguish cats from not cats if they were trained on this task. Okay, and similarly for all of these other subgroups. Now, the definition of good subgroup depends on the training procedure used. So cats might be a good subgroup for ResNets, but may not be a good subgroup for weaker classifiers like MLPs or even ResNets trained on fewer samples. So this definition of good subgroup is crucial. Notice that in a given setting, there could be many good subgroups for a given training procedure. So cats, animals, objects, even things which don't depend on the label. And the training procedure doesn't know about these subgroups, right? So we only trained on this binary task in this example, but the classifier that was produced was automatically calibrated with respect to all of these subgroups. So also a conjecture is a sort of subgroup calibration that predicts the kinds of calibrations that a classifier will satisfy based on its properties. So here's an example application of the conjecture that looks a bit different from the previous experiment. Let's consider ImageNet, which is a 1,000 classification problem, including more than 100 different types of dogs. Now, this is a hard problem, and AlexNet only gets 56% test accuracy on this 1,000 class problem. But we could ask, okay, 56% doesn't sound very good, but does it at least classify dogs as some type of dog? Does it at least have this structure? So if we feed in an image of a German Shepherd, for example, will AlexNet at least classify it as some other kind of dog instead of labeling it as, say, some houseplant? And in fact, this does hold. So 98% of the time, if you input some image of a dog, it will output some dog label. You might get the exact breed wrong, but it will be some kind of dog. And this is actually a very nice structure, right? Because it says that even though AlexNet has low accuracy on this overall fine-grained problem, if we zoom out, then it actually has high accuracy at the appropriate group level. And this is the kind of behaviors that are actually exactly predicted by our conjecture. And it shows that a conjecture can reveal good structural properties of classifiers that are not revealed by just looking at test error. In fact, even classifiers with high test error can have good structure in certain other senses. Okay, so this was just a very brief overview, but please see our paper for much more formalism, details, experiments, and more conjectures and open problems. Thank you.